Safety at close range, proximity, force control, and collision response. As of August 9, 2026, collaborative robot safety is no longer based on one feature. A safe robot needs several layers working together. Good mechanical design, accurate torque or force sensing, fast collision detection, controlled stopping and recovery, reliable human detection, and safety certification for the full application. This article presents an evidence-based evaluation of impedance and admittance control, torque sensing, collision thresholds, 3D speed and separation monitoring, reaction time, residual force, recovery behavior, and certification evidence. Important scope note: public robot documents do not provide one common, independent test report for every robot. The comparison below uses public manuals, safety documents, product data, and research from standards bodies. A real purchase decision should still include hands-on testing with the exact robot, tool, payload, software version, and work cell. Executive summary. The main findings are: direct joint torque sensors usually provide better contact information than motor current estimates, but they do not remove the need for good calibration and filtering. Impedance control is usually the better choice for robots with low-level torque control and direct joint torque sensing. Admittance control is often easier to add to a position-controlled robot, especially when using an external wrist force torque sensor. Collision thresholds are not injury limits. A robot can stop quickly and still create too much force if speed, payload, tool shape, or body location are not controlled. Speed and separation monitoring is often safer than waiting for contact. However, a normal RGBD or AI camera should not be treated as a safety device unless the complete system is safety rated. 3D safety cameras are becoming available, but many products still have lower safety ratings than the robot controller. The complete system must be designed around the weakest safety link. KUKA LBR IEWA, Franca Research 3, ABB GOFA, and Doosan Cobots provide strong public evidence for torque-based contact control. ABB SafeMove, FANUC Dual Check Safety, Universal Robot Safety Functions, and safety scanners provide mature tools for separation monitoring. Certification does not certify the whole work cell. The end effector, payload, workpiece, software settings, speed, human access, and recovery behavior must also be assessed. The current safety rulebook. The main international standards have recently changed. ISO 10218-1 2025 covers the safety of the industrial robot itself. ISO 10218-2 2025 covers the complete robot application and cell, including integration, commissioning, operation, and maintenance. These standards replace the older 2011 editions. ISO TS 1566-2016 remains the main technical reference for collaborative robot operation. It covers 4 common collaborative methods: safety-rated monitored stop, hand guiding, speed and separation monitoring, power and force limiting. ISO TS 1566 was reviewed and confirmed in 2022. A new work item, ISO AWI 1566-1, was registered in June 2025 and is intended to replace the current technical specification, but it is still under development as of August 2026. Other important standards include ISO 13849-1 2023 for safety-related control systems, ISO 13855-2024 for the position of safeguards and approach distances, ISO 13857-2019 for safety distances that prevent access to danger zones, and ISO 12100-2010 for risk assessment and risk reduction. These standards make one point clear: robot safety is a system problem, not just a robot feature. Impedance and admittance control. What is impedance control? Impedance control tells the robot how strongly it should resist movement. For example, a robot can be programmed to behave like a stiff metal bar, a soft spring, a spring with damping, a light object that moves when touched. The controller creates a relationship between position error, speed, and force. When an outside force pushes the robot reacts according to its programmed stiffness and damping. Impedance control is closely linked to torque control. It works best when the robot provides fast torque control, accurate joint torque feedback, low mechanical friction, a well-calibrated robot model. The basic idea was developed in early robot interaction research by Neville Hogan, who showed that controlling the relationship between force and motion is more useful for contact tasks than trying to control position or force alone. What is admittance control? Admittance control works in the opposite direction. It measures an outside force and converts that force into a change in position or speed. For example, a person pushes the robot arm. A force sensor measures the push. The controller moves the robot in the direction of the push. Admittance control is common on robots that mainly use high-gain position control. It can be added with an external wrist force torque sensor or another force measuring device. Research describes admittance control as a practical choice for geared, position-controlled robots because it turns measured force into a position command. Impedance versus admittance. For the full table, please open this article on robotcomparisons.com. Which one is better for safety? Neither method is automatically safer. Impedance control can provide a more natural response when the robot has accurate joint torque sensors and a fast internal controller. This is one reason KUKA, Franka, and ABB place strong emphasis on joint torque sensing. Admittance control can work well on larger or more traditional robots, but the result depends on force sensor location, sensor bandwidth, filtering, outer loop update rate, position controller delay, payload and friction compensation. A slow admittance loop may allow the robot to push too long before it moves away. A badly tuned loop may also create vibration or overshoot. The best test is not simply does the robot move when pushed. The test should measure peak force, time before movement begins, motion overshoot, settling time, oscillation, repeatability, behavior with different payloads, behavior at different arm positions, torque sensing quality, direct torque sensing versus motor current estimation. Robots can detect contact in two main ways. Direct torque sensing measures twisting in the joint or transmission. The sensor may use strain gauges or another mechanical measurement method. Motor current estimation estimates torque from motor current. This is less expensive and is widely used, but it depends more heavily on a robot model. Motor current methods must separate external contact from gravity, friction, gear resistance, acceleration, payload changes, temperature drift, cable forces, model errors. NIST research warns that electrical current sensors can drift. That drift can create inaccurate joint torque and end effector force readings during a human-robot collision. This does not mean current-based detection is unsafe. It means the system needs good calibration, temperature compensation, payload identification, speed-dependent thresholds, fault monitoring, regular validation. What makes a torque sensor good? A useful safety sensor should be tested for resolution, noise, drift, bandwidth, latency, cross-axis error, payload sensitivity, pose sensitivity, fault behavior, calibration evidence. A direct torque sensor is usually a strong starting point. However, direct sensing alone does not prove that the robot will create safe contact forces. Public comparison of real robot platforms. The following comparison uses public product and safety documents. It is not an independent laboratory ranking. For the full table, please open this article on robotcomparisons.com. Best choices by application. Most contact-focused and research-friendly, Franka Research 3. Strong industrial force control, KUKA LBR-III. Balanced industrial cobot platform, ABB GOFA. High flexibility and collision zones, Doosan Robotics. Broad industrial ecosystem, FANACRX, or Universal Robots. High throughput collaborative direction, ABB POA, with careful validation of the exact safety configuration. These are not absolute winners. A robot that is excellent for delicate assembly may be a poor choice for heavy machine tending. Payload, tool shape, stopping distance, and work cell layout matter just as much as the robot arm. Collision detection thresholds. What is a collision threshold? A collision threshold is the point at which the controller decides that an unusual force or torque is present. Some robots use joint torque thresholds, Cartesian force thresholds, TCP force limits, power limits, momentum limits, speed limits, position limits, separate contact and collision levels. Franka, for example, allows separate lower and upper thresholds. A lower threshold can identify contact, while a higher threshold can trigger a stronger collision response. Its documentation also warns that external force estimates can become less accurate during fast or abrupt motion. Doosan provides configurable collision sensitivity and different responses for collaborative and standalone zones. Its documentation also describes crushing prevention zones with very sensitive collision settings and a reflex stop. Universal Robots documents TCP force limits, joint torque limits, power limits, momentum limits, and stopping limits. Its reduced safety configuration can be activated by a safety input or a safety plane. Why thresholds are difficult to tune. A threshold that is too low can cause false collision stops, stops during acceleration, stops caused by cable drag, stops during insertion or gripping, poor production uptime. A threshold that is too high can cause longer contact before stopping, higher peak force, greater risk of pinching, more damage to parts or tools. Unsafe response when the robot carries a heavy payload. Thresholds should be tested with empty tool, maximum payload, minimum payload, long and short tools, different arm poses, different robot speeds, warm and cold operating conditions, hard and soft contact surfaces. A good system uses speed, pose, payload, and direction-aware limits rather than one fixed number for every condition. Speed and separation monitoring with 3D perception. Why separation is better than contact. Power and force limiting waits until contact begins. Speed and separation monitoring, or SSM, tries to prevent contact before it happens. The robot slows down or stops as a person enters the protected area. NIST describes the protective distance as a combination of human movement during the reaction time, robot movement during the reaction time, robot stopping distance, allowances for sensor intrusion and uncertainty. A simplified form is, NIST research provides a formal version of this calculation and stresses that robot stopping speed and sensor uncertainty must be included. 3D safety cameras available today. A useful commercial example is SICK Safe Visionary 2. It is a 3D time-of-flight safety camera with PLC, SIL1 Type 2 classification, up to 4 meters of protective field range, 2 protective fields, 8 monitoring cases, a published response time of at least 55 milliseconds, depending on configuration. SICK positions it for 3D protection around collaborative robots, including detection of upper bodies and upper limbs. ABB also provides collaborative speed control tools that combine SafeMove with safety laser scanners. ABB states that the robot controller needs an external safety sensor to know where a person is located. This is an important point. The robot may be safety rated, but it cannot detect a person who is outside its own sensing system. Is an AI camera safe enough? An AI camera can identify a person, a hand, a head, a worker's pose, a person's direction of travel, a likely future path. This can improve productivity. For example, the robot may slow down only when a person is truly approaching the danger area. However, a normal AI camera may fail because of occlusion, poor lighting, reflective clothing, dust, network delay, camera movement, multiple people, a person entering from an unseen direction, incorrect body part tracking. For this reason, AI vision should normally be treated as a productivity and planning layer, unless the complete detection, logic, communication, and robot stop chain has been safety certified. Recommended 3D perception test. A proper SSM test should include the following cases. Human movement tests. Test a person walking toward the robot, walking across the robot's path, approaching from the side, approaching from behind the robot, leaning into the work area, reaching with one hand, crouching, wearing loose clothing, carrying a box or tote, moving with another person nearby. Visibility tests. Test full visibility, partial body occlusion, occlusion by a workpiece, occlusion by a cart, a person behind the robot. Changing light levels, reflective surfaces, dust or light haze, camera lens contamination, temporary camera signal loss. Measurements. Record time when the person enters the detection field, time when the camera first reports the person, time when the safety controller changes robot speed, time when the stop signal is issued, time when robot speed begins to fall. OBOT reaches a safe stop, minimum measured human-robot distance, false stop rate, missed detection rate, behavior after sensor failure, use synchronized timestamps from the 3D camera, the safety PLC, the robot controller, joint encoders, an independent high-speed camera, and a separate position tracking system. The key result is not the average reaction time. It is the worst-case reaction time, including network delay, filtering, decision time, drive response, and mechanical stopping. Reaction time and residual force testing. Do not test on a person. Contact testing should use a biofidelic force and pressure device, not a human volunteer. NIST has developed measurement methods and soft sensors designed to represent how human body regions deform during robot contact. These systems can measure dynamic force, static force, pressure, and deformation, without putting a person at risk. Reaction time should be split into 4 parts. Measure these separately. Detection time, how long it takes to detect unusual force or a person. Decision time, how long the controller takes to decide on a response. Drive response time, how long it takes the motor system to reduce torque or speed. Mechanical stopping time, how long the arm takes to stop moving. A vendor's claim that a robot stops in milliseconds is not enough. The important number is the full end-to-end time, from the start of unsafe contact or unsafe approach until the robot has stopped or reached a safe reduced speed. Contact test conditions. Test contact at low, medium, and high speed. Several robot poses, several payloads, several tool shapes, different contact directions, different arm sections, the wrist and tool, hard and soft surfaces, static pushing, sudden impact, sliding contact, pinching contact. Force and pressure measurements. Record. Peak force, peak pressure, average force, force duration, impulse, stopping distance, residual force after the stop, rebound force, force caused by gravity after the stop. A useful reporting format is, this reveals whether the robot truly releases energy or simply stops while continuing to press against the object. Collision recovery behavior. Stopping is only half of the safety story. The robot must also recover safely. Common recovery types. Protective stop. The robot stops and waits for a reset or operator action. Reflex stop. The robot quickly reduces torque or moves slightly away from contact. Retract. The robot reverses direction after hard contact. Push to escape. The robot can be moved away manually after a collision. Safe operating stop. The robot holds position with power applied. Power off stop. Drive power is removed. FANUC, CRX public material describes contact stop, push to escape, and immediate retract after contact with hard objects. Doosan documents an RS1 reflex response and special crushing prevention zones. Universal Robots distinguishes emergency, safeguard, and enabling device stops, each with different stop and reset behavior. Recovery tests. For every collision or proximity event, test. Does the robot remain stopped while a person is still present? Can the robot restart without a clear reset? Is a manual reset required? Does the robot move away from the contact? Can the operator safely push the robot away? Are brakes applied? Is stored mechanical energy released? Is the program position preserved? Does the tool remain active? Does the gripper release its load? Can the robot resume without repeating the hazard? A safe recovery should be predictable, slow, and easy to understand. Tuning flexibility versus certification. There is a clear trade-off between flexibility and certification. High tuning flexibility. Platforms such as Franker Research 3 and Doosan Robotics expose many settings for stiffness, damping, force limits, torque limits, collision sensitivity, safety zones, stop modes, recovery behavior. This is useful for research, delicate assembly, and changing workpieces. It also creates more responsibility for the integrator. More controlled tuning. Platforms such as Universal Robots, ABB SafeMove, and FANUC provide many configurable limits, but their safety functions are more tightly controlled through safety menus, passwords, certified controllers, safety options, and external safety devices. This can make deployment easier for a business owner because the system is more structured. It may also limit the ability to experiment with very low stiffness or unusual contact behavior. Certification evidence hierarchy. When comparing vendors, look for evidence in this order: independent safety certificate, safety manual with exact model and software version, published PFH or PFHD value, defined stop category, defined performance level or SIL, documented safety input and output behavior, validated configuration limits. Only then marketing claims. Public examples include UR safety functions rated PLD category 3 with PFHD values below 1.8 times 10-7 per hour. KUKA LBR IEWA safety functions rated PLD category 3 with functional safety up to SIL 2. Franker Research 3 documentation listing PLD category 3 functions and external device SSM capability up to that level. Doosan safety monitoring functions documented as PLD category 3 SIL 2 in its current manuals. FANUC documentation listing collaborative robot safety functions and dual check safety functions at category 3 PLD for applicable controller versions. ABB GOFA documentation listing category 3 PLD collaborative safety. These ratings are not directly interchangeable. They may apply to different safety functions, hardware versions, software versions, or operating modes. Practical advice for businesses. For small and medium-sized manufacturers, choose a system with simple safety setup, clear safety menus, strong local support, a large integrator network, easy reset and recovery, published safety manuals, available safety scanners or 3D sensors. Universal Robots, FANUC CRX, ABB GOFA, and Doosan are practical starting points for many small and medium-sized applications. For delicate assembly, look closely at direct torque sensing, low stiffness impedance control, force repeatability, calibration quality, contact detection during slow insertion, recovery after a failed insertion. KUKA, LBR, IEWA, and Franker Research 3 are strong candidates for this type of work. For fast machine tending, speed and separation monitoring may be more useful than allowing frequent physical contact. Consider ABB SafeMove, FANUC Dual Check Safety, Universal Robot Safety Inputs and Reduced Modes, Safety Scanners, 3D Safety Cameras, clearly defined stop and restart zones. For high-speed collaborative robots, the newer ABB POA family is designed to combine collaborative behavior with higher industrial speed and payload. ABB states that POA includes built-in power and force limiting and speed and separation monitoring with global availability in 2026. However, the exact model, tool, payload, external safety devices, and certification documents must be reviewed before using a fenceless design. For dangerous tools, a collaborative robot arm does not automatically make a dangerous application safe. Extra protection may be needed for blades, grinders, welders, drills, high-temperature tools, sharp parts, heavy workpieces, high-pressure systems, parts that can fall or break. The risk assessment must include the tool and workpiece, not only the robot arm. Recommended acceptance test. Before production use, require the integrator to provide robot model and software version, safety certificate, declaration of conformity, safety manual, PFH or PFHD values, stop category, maximum stopping time, maximum stopping distance, collision threshold settings, force and pressure test results, 3D camera or scanner response time, minimum protective distance calculation, sensor failure response, power loss response, restart logic, tool and payload risk assessment, test records for every robot pose and operating mode. A system should not pass simply because the robot stops when touched. It should pass only when the robot detects the event reliably, the force remains within the required limit, the robot stops in time, the safety sensor does not miss people, the robot does not restart unexpectedly, the behavior remains safe with the real tool and payload. The near future of close-range robot safety. 3 trends are likely to shape the next few years. More safety-rated 3D perception. Safety-rated 3D time-of-flight cameras are already available. Future products should offer larger protective fields, better upper limb and head detection, better occlusion handling, lower response time, higher safety ratings, easier integration with robot safety controllers. AI is a productivity layer. AI will likely help predict human movement and reduce unnecessary stops. It may allow a robot to slow down only when a person is moving toward the danger area. However, a sensible safety design will keep the final stop decision inside a deterministic, safety-rated system. AI can improve speed and comfort, but it should not be the only barrier between a person and a moving robot. ABB is already linking newer robot platforms with AI-powered tools, vision systems, analytics, and digital software. This shows where the industry is moving, even though the safety function still depends on certified controls and protective devices. Better test standards. The work on ISO AWI 150661 shows that collaborative safety limits and test methods are still developing. Future standards may provide better guidance for body part-specific impact testing, dynamic human movement, 3D camera uncertainty, AI-based human tracking, robot recovery behavior, shared mobile robot workspaces, and higher-speed collaborative operation. Conclusion. The safest close-range robot is not simply the robot with the lowest collision threshold. The strongest system combines direct and well-calibrated torque sensing, fast impedance or admittance control, speed and separation monitoring, safety-rated 3D perception or scanners, low residual force, predictable recovery, clear certification evidence, and a complete application risk assessment. For contact-rich work, KUKA LBR IIIA and Franca Research 3 offer especially strong public evidence for torque-based control and tuning flexibility. ABB GOFA and Doosan provide a good balance between force sensing, configurable safety zones, and industrial use. FANUC CRX and Universal Robots offer mature industrial ecosystems and well-documented safety functions. For fast shared workspaces, ABB SafeMove, POA, FANUC DualCheck Safety, and safety-rated scanners or 3D cameras deserve close review. The final decision should be based on measured results, not marketing words. Test the exact robot, exact tool, exact payload, exact software version, and exact human work pattern before allowing close-range operation. All links to sources are available in the text version of this article. You can find the full article at robotcomparisons.com/blog. Thanks for listening. Thanks for listening to Robot Comparisons. If you found this episode valuable, make sure to subscribe so you never miss a new deep dive. For the full written breakdown, detailed spec sheets, and side-by-side comparisons, head over to robotcomparisons.com. That's ROBOTCOMPARISONS.com. New research drops multiple times a week.